From code to execution, programs, processes, and the operating system. In the previous lecture, we established that a backend workflow is a sequence of state transformations. Today, we study the first irreversible one. Code becomes execution. Most backend engineers spend their days writing source code, but production incidents almost never come from code as text. They come from code as a running process. So the first question a senior backend engineer must be able to answer is not, what does this code do? But, what is actually running? Let's start with a hard truth. A program does nothing. A program is a static object. It sits on disk. It has no memory, no CPU, no ability to affect the world. It is inert. Only when the operating system gets involved does anything real happen. When you start a service, the operating system takes that inert program and creates a process. A process is the moment where your code becomes dangerous, in a good way. A process has memory assigned to it, CPU time scheduled for it, open files and network sockets, and most importantly, consequences. Here is the boundary most engineers never fully internalize. Your code does not control execution, the kernel does. The kernel is not a library. It is not part of Linux in an abstract sense. It is the only component allowed to touch hardware, schedule CPU time, manage memory, and isolate processes from each other. Your backend service runs in user space, which is a restricted execution environment. User space code cannot access hardware, read arbitrary memory, or control other processes. Every time your service wants to do something real, read a file, open a socket, allocate memory, it must ask the kernel politely. That request happens through a system call. A system call is a controlled crossing of the most important boundary in backend systems: user space, kernel space. This boundary exists for one reason: damage containment. If your service crashes, leaks memory, or loops infinitely, the kernel survives. If the kernel crashes, the entire machine dies. This is why privilege separation exists. Most backend bugs are survivable precisely because your code runs with limited authority. Now let's talk about time. A process does not run continuously. It is scheduled. The kernel rapidly switches between processes, saving and restoring their execution state. This is called a context switch. From your code's point of view, it feels like continuous execution. From reality's point of view, your service is sharing the CPU with everything else on the machine. This is where many performance myths die. Your service does not own the CPU. It borrows it. Latency spikes, throughput collapse, and tail delays often originate here, not in your business logic, but in how execution is scheduled. Understanding this is the moment you stop blaming the cloud and start debugging reality. Mental models, non-negotiable. A program is inert. A process is active and dangerous. The kernel is the true execution authority. User space code cannot bypass the kernel system. Calls are controlled boundary crossings. Your process does not own the CPU. It is scheduled. Most production bugs are execution bugs, not logic bugs. Common senior-level failure pattern. The code looks fine. I don't see why it's slow. If you are not asking how many processes are running, how often context switches happen, whether the process is runnable or waiting, then you are debugging text, not execution. Why this matters for workflow. This lecture explains why deployment is not the end of risk. The moment code becomes a process, resource limits matter, scheduling matters, isolation matters, and failures become physical, not abstract. From this point forward, every workflow decision must respect one fact. Once code is executing, the operating system is your most important dependency.